Think forward. Think Research Channel.
The opinions expressed in the following program are strictly those of the speaker. They do not necessarily reflect the views of the National Science Foundation.
From the National Science Foundation, where discoveries begin. This is Frontier. Discussions of today's most exciting research subjects by distinguished scientists and engineers working at the frontiers of knowledge.
Chaos. From the fiery collision of neutron stars to the eruption of a supernova, cataclysmic events leave behind clues about the fundamental nature of matter and energy, even the origins of time and space. According to Einstein, space-time is like a fabric, and what we call gravity is the warping of this fabric by a massive object, like a star. It's an astonishing idea, and it led Einstein to a prediction that when a massive object collides with another, or changes speed or direction, it produces waves in the fabric of space-time. Gravity waves. Like ripples on a pond, these waves travel outward from their source, carrying information about the events that cause them. Racing at the speed of light, they are the ultimate cosmic messengers. Einstein's messengers. Now, at Twin Labs in the heart of Louisiana and in the high desert of Washington State, dedicated teams of scientists and engineers are undertaking one of the great technological challenges of the new century. It's called LIGO, short for Laser Interferometer Gravitational Wave Observatory, the result of years of pioneering research. LIGO is funded by the National Science Foundation and operated by the California Institute of Technology and the Massachusetts Institute of Technology.
Most of what we know about the universe comes from electromagnetic radiation. LIGO as a project is important because it's going to potentially open up a new window on the universe.
LIGO is the work of hundreds of scientists, engineers, and students. The LIGO Scientific Collaboration, based at the labs and at dozens of universities around the world. It consists of two widely separated installations within the United States, operated in unison as a single observatory. Each LIGO lab is the world's most precise measuring stick, made up of two arms extending 4 kilometers in length. Measurements are performed by bouncing powerful laser beams back and forth between highly polished mirrors located in each arm. Any passing gravitational wave will move the mirrors by a distance thousands of times smaller than the width of an atom. This displacement will throw the beams very slightly out of phase with each other, which will reveal the form of the passing wave. LIGO scientists have always known that to detect a gravity wave from space, they'd have to isolate the signal from the noise on Earth. And they've worked painstakingly to do that. Still, some local events, like thunderstorms, micro-earthquakes, and certain man-made noises, can cause mirror displacements that could be misinterpreted as gravitational wave events. That's why two detectors, located at widely separated sites, are essential. If both labs pick up the same signal at the same time, chances are it's not noise from Earth, but a gravitational wave from space.
It's a big challenge. In some sense, you could describe it as a high-risk experiment. Oh, but the payoff is enormous.
The more sensitive scientists can make LIGO, the more distant the signals they can detect. LIGO is currently designed to track events out to 300 million light years, a volume of space containing 100,000 galaxies. But when the interferometers received their first major upgrade, in a project called Advanced LIGO, their range will extend out to 5 billion light years, about a third of the way to the edge of the visible universe.
And that combination of the observations that we make together with numerical simulations, I expect, will revolutionize our understanding of general relativity and its consequences.
If the team can track down these titanic explosions, they can go after the biggest explosion of them all. LIGO holds this amazing potential to go back to the beginning, to the first moments of space and time, the Big Bang.
Takes you all the way back to the instant of creation. Now imagine such a concept. Now, nobody's guaranteeing us that we will see something from that. But gravity waves are the only way you will get information from that epoch. That alone is a justification for doing everything you can to try to detect them.
Members of the LIGO scientific collaboration are honing their computer programs to handle the flood of data. Meanwhile, other observatories are also being launched in Europe, Australia, and Japan. They'll work with LIGO to calculate exactly where signals are coming from. And a planned space-based detector could complement the Earthbound systems. The hope is this new science will take physics even beyond Einstein's great theory, and one day yield discoveries about space and time as fundamental as the discovery of the atom. As the search for gravity waves begins, LIGO is inspiring kids and adults alike. Stargazers like these are actually becoming part of the action.
Oh, cool.
Because the LIGO team needs such vast computing power, it's turning to homes with computers all across the country, tying them together in a vast network. Anyone who wants to help can join the search for gravitational waves through a project called Einstein at Home.
Gravity waves are rumbles in space that they're searching for. They look for them a lot.
From these ranks may well come the next generation of gravitational wave explorers.
I hope I never stop stepping back and looking at the big picture and saying, instead of trying to get this one piece of electronics to work, I'm trying to detect gravity waves. And that's something that, when you stop and you think about that, there's a moment of wonder there. You say to yourself, what on earth am I doing here? This is incredible.
I think that's what characterizes many scientists. They are people who never lost their childlike wonder about the universe, and they're still driven by that childlike wonder.
History has shown the great discoveries in science usually occur when revolutionary instruments provide new means to explore the universe. LIGO gives us a fresh set of eyes, an entirely new way to uncover the universe's deepest mysteries. LIGO will open whole new branches of scientific research and technological achievement.
So gravitational waves, for those of you who are not deeply into this business, are actually ripples in the fabric of space-time, the fabric of space-time that Einstein postulated in his general theory of relativity. And these ripples propagate in space-time at the speed of light. And so you can think of them as waves in the very fabric of space and time. These waves are transverse waves. So here's some pictures. If a wave is coming towards you, the oscillations in the wave are transverse to the direction of motion, and they're quadrupole waves. They have this fourfold shape to them. They're polarized with two polarizations, and their impact on space is to alternately stretch and squeeze as they come by. So if a gravitational wave was going into this slide, space would alternately stretch up and down, longer up and down, skinnier transverse, and then the other way around. So I guess I can go like this. So if a wave is coming at you, space will stretch this way, and that's the phenomena we will try to detect with LIGO. These gravitational waves will be emitted by accelerating aspherical mass distributions. Mass distributions that are not spheres, that are lumpy in some different ways, and that are moving. And the faster they're moving and the more mass that's moving, the larger the strength of the gravitational waves. You'll see that in a few minutes. For astronomy, one of the important facts to remember is that these are waves in space-time. They're not absorbed as they pass through objects. And so if you're using them in some way to see far out into the universe, your view isn't impeded because the gravitational waves just come right to you. Okay, so let's talk about a few sources of gravitational waves. Okay, well, things are a little bit out of order, but one is periodic sources in our galaxy, pulsars. Pulsars are spinning objects. If they're not spherical, if they have a lump on them, for example, as they spin, they emit gravitational waves, and we should be able to see gravitational waves in phase with the spinning of the pulsars. So that's one possible source in our galaxy. A very important source for us are coalescing compact binaries. Basically, objects that involve two massive objects, like a pair of neutron stars or a pair of black holes, that are orbiting around each other and spiraling in towards each other. And in fact, if you look at this cartoon, this represents the three stages in the life of one of these objects. They're spiraling around each other, they get closer and closer, and at a certain point they touch and merge. And as this happens, especially in the latter stages, gravitational waves are emitted that can get very strong with a pattern that is determined by the characteristics of the source, the mass, the speed of orbit, things of that sort. So this is a class of astrophysical object that will emit gravitational waves, and we can learn about them by the shape of those waves. There are burst events. For example, if there's a supernova in our galaxy that is not spherical, that will emit a burst of gravitational waves that we should be able to detect. And lastly, there's something we call stochastic background. It's sort of a burbling of gravitational waves coming from all directions. And this kind of signal, if it exists, will come from two things. One, it would be just a continuum of sources, many sources out there that are each contributing. But more interesting, in principle, are gravitational waves from the Big Bang itself. And these gravitational waves are really a unique way to probe to the very beginning of, right after the Big Bang. Time is something like 10 to the minus 22 seconds after the Big Bang. And so, unlike photons and neutrinos, this would probe to the very, very earliest stages of the universe. And the unexpected, of course. That's probably going to be the most exciting thing when the time comes. Okay, so I want to give you an estimate of the strength of gravitational waves, because this sets the scale for the experimental challenge. So this formula, it's the only formula I'll show you, indicates the strain in space-time generated by, by I double dot, which is a quadrupole mass distribution. And so it's the second derivative of a quadrupole mass distribution. This strain can be approximated here, and the important thing to see in this formula is that there is a very tiny number in the numerator, g, the strength of gravity, and a very big number in the denominator, the speed of light to the fourth, and the distance to the source. And so this means that h is going to be a very small number. And so, for example, here's a pair of neutron stars. If we have a neutron star pair in the Virgo cluster, each with a mass of 1.4 times the mass of the sun, if you plug in the numbers, you get a value for h of 10 to the minus 21. H is a strain. It's the fractional change, stretching or compressing of space-time. And so, if I want to measure how much this gravity wave from this source would change space-time over this distance, I have to measure 10 to the minus 21st of this distance. It's an incredibly tiny amount. So, oops, back one. So the way we do this is by using precision interferometry. This is sort of a cartoon of how LIGO works. There's a laser which generates light laser light that hits a beam splitter. Half the light goes this way, half the light goes this way. The light bounces off of mirrors, goes back and forth, and then comes back to the beam splitter and recombines. And if the distance the light travels in this direction is exactly the same as the distance in this direction, when that light recombines, you get no light coming out at the sensor, the photodetector. If, however, these distances are unequal, the interference isn't exact and you do get light. So the light you get coming out of the interferometer is a measure of the difference in the distance the light travels in this arm compared to this arm. And so if you imagine a gravity wave shown here coming down onto the interferometer, it will alternately stretch and compress one arm compared to the other. And so you'll get a signal coming out which goes positive, negative, as that gravity wave stretches one arm, compresses the other, and changes the other way around, So this is the principle for LIGO. Interferometry is a very sensitive technique, and so it allows us to measure these relative distances as a function of time with very, very high precision. And so let's look at some numbers here. So experimental challenges and limitations. As I said before, the amplitude of the gravitational waves, the strain, which is the differential change in length, is something like 10 to the minus 21st from a typical source out there in the heavens. LIGO is a huge interferometer. The arms are 4 kilometers in length, 2.5 miles. And so if we want to measure a differential strain over something that's 4 kilometers long, multiply these two, and we're looking at a change in length of about 10 to the minus 18th meters. And so to detect gravitational waves, LIGO has to be able to measure changes in the spacing, the relative spacing of these mirrors in the two different arms. The mirrors are miles apart. We have to measure the difference, a change in their separation by about 10 to the minus 18th meters. For those of you who are in nuclear particle physics, that's 1,000th the size of a proton. If you like astronomy, that's like trying to measure the distance to the nearest star to an accuracy of a hair's width. It's incredible precision. Okay, and so that's the real challenge. Of course, it is hard. What makes it hard, of course, are the fact that, first of all, the effect is very, very tiny. But also, as you can imagine in the real world, if you have two mirrors a couple of miles apart, there are external forces that push the mirrors around. Thermal fluctuations, the trucks go by, the ground jitters, and such things. And then there are fluctuations in the laser light that we're putting into the interferometer to do the measurement. Fluctuations in the light can appear like fluctuations in the measured separation of the mirrors. So the question is, how can you, and I should say, before I joined LIGO, I never believed LIGO would work, because I couldn't believe you could measure things to this accuracy. Rich, you're looking at me. I was on one of your committees once. And I came away and I went home and I told my family, this has just never happened. So finally it was explained to me how it works. It works. And the secret is having lots of photons in the laser light. Because with lots of photons, in effect, you're measuring where that surface of the mirror is many, many times simultaneously. And you average over the surface of the mirror. You average over the fluctuations in all the atoms of the surface by probing it huge numbers of times. And huge numbers of times is a fact that during the time we make a measurement for one cycle of a gravitational wave, there are about 10 to the 21st photons that hit the mirror. And the statistical accuracy of trying to measure something depends on the square root of that number. And so with enough photons, with a powerful enough laser, you can actually measure these very precise distances. So here's a little formula. The strain, which is delta x over L, depends on the wavelength, on the effective arm length, which is not 4 kilometers, I've told you, but it's about 50 times that, because the light typically bounces back and forth between those mirrors 50 times. So it's like having an arm length 50 times longer. The square root of the number of the photons times the amount of time we're making the measurement, one wavelength of the gravitational wave. If you plug in the numbers, that comes out something like 10 to the minus 21. So it is doable in principle, and it's also doable in practice. And so in practice, you then deal with more than just the number of photons. You deal with all of the things that can jiggle the mirrors, all the things that can create noise. And there's a whole long list of these kinds of things, but I want to give you a sense of the most interesting ones. So this plot shows the sensitivity, the strain sensitivity, the number I've just talked about, or something related to it, the frequency at which we're making the measurement, and this, this orange line is the sensitivity of LIGO. It goes down and then comes up, and there's a nice sweet spot here. And all these curves represent different sources of noise or perturbations. And I've characterized them in four different categories. One is displacement noise, things that cause these mirrors to jiggle or move. One is seismic motion, just plain old ground motion from the tide hitting the shore, from trains coming by, from trucks hitting a bump in a nearby road, you name it. And that's a limit on low frequencies, and you see the seismic limit over here. So below about 40 hertz, the sensitivity of LIGO gets much worse very quickly, and we can't measure there. There's thermal noise, just the vibrations in those mirrors because they're at a finite temperature, Brownian motion, if you will. That's shown here. Here's the thermal noise in the wires that hold the mirror. They're like pendulums, and you can see in this area that's the limiting factor. And then there's radiation pressure, just the sort of the laser light shining on the mirror. It's not completely constant. It's like rain hitting a roof, and that jiggles the mirrors around. And here's radiation pressure down here. Then there's sensing noise. This is shot noise. It's simply the photon counting statistics in making the measurement. And that's the effect that limits us at high frequencies, above about 100 hertz, going up here. And these are the quantum fluctuations in the number of photons we detect. So those are the three factors that give you this curve. There are other limits. One is scattering of light on the gas in the arms. Those arms are in very large vacuum chambers. I think the total vacuum volume is about the equivalent of the inside of 10 747s at a temperature of 10 to the minus 9th torr. That's down here. So we're far away from that limit. But you do have to evacuate the arms of the interferometer. And then there's an intrinsic limit, which is interesting, which is this curve over here. Basically, the surface of the Earth moves due to various things. And if the surface of the Earth is moving near the instrument, the gravitational potential on those mirrors changes. You can't shield that. And so that's not the ground moving and moving supports and moving the mirror physically by physical connection. It's simply the gravitational potential making very small changes just because the shape of the Earth's surface changes. And that's this curve. And you can't get away from that. And just to comment, that's the reason to look for gravitational radiation at very low frequencies. You have to go into space. This cuts you off at 10 or 1 hertz. LISA, the space mission that's being proposed, would go down to much lower frequencies. That's why they have to go into space. It's this effect. Okay, how do we avoid fooling ourselves? I don't want to spend a lot of time on this, but as I've indicated, there are lots of things that can give you a false signal, and we go to great lengths to avoid that happening. And so, as you'll see in a minute, we have interferometers at 2 sites, at 2 different parts of the country. So we look for coincidences, essentially, a signal in both. So it's not some local disturbance. We look at our data with certain constraints in mind. If we're looking for a pulsar, we know the frequency of the pulsar. If there's a gravitational wave signal, it better be in phase with that. We have a huge number of environmental monitors, seismometers, accelerometers, wind monitors. We look for ground jiggling, we look for wind, we have microphones to look for noise that could jiggle things around, we measure magnetic fields on the site, we measure the line voltage, we measure everything we can. So that if we think we see a signal, we want to make sure it's not in coincidence with some external disturbance that has nothing to do with gravitational waves. And then we make sure periodically we inject signals into the system that should come out the other end, that look like gravitational waves, to check the hardware, to check the analysis, and so on. So that's a big part of what we do. This experimental challenge I've described is something that's engaged LIGO people for almost a decade now. And after LIGO itself was constructed, there was 5 years of very intense effort to reduce the noise, to bring the sensitivity down by something like 3 orders of magnitude. I mean, people did amazing things that I'm in awe of. I couldn't have done it. And I'm learning about them more and more. The good news is that about a year ago, the design sensitivity of LIGO that was predicted in 1995 was reached. And so this curve, the yellow curve, is the predicted sensitivity from 1995, and these other curves are the sensitivity reached by the interferometers in LIGO about a year ago. And so this was a great achievement, getting down to what was predicted all those years ago. And this is the basis now for the science run we're starting on. So the next few slides are a few pictures of LIGO. So we're going to talk a little bit about LIGO itself now. These photographs show the two LIGO sites, one in Hanford, Washington, up here, where we have two interferometers, one 4 kilometers long, one 2 kilometers long. You can see the very long arms stretching out to the distance. The other in Livingston, Louisiana, where we have a single 4-kilometer interferometer. You can choose deserts or swamps. But we have these two sites separated by about 3,000 kilometers, so we can get independent coincidence measurements. I should tell you the groundbreaking for LIGO was in 1995. The first of these interferometers to start actually functioning as an instrument was in 2000. LIGO is managed and operated by Caltech and MIT under a cooperative agreement with NSF. So we thank NSF, of course. And there's an international scientific collaboration called the LIGO Scientific Collaboration that has about 45 institutions, about 500 scientists worldwide that help us operate the interferometers, analyze the data, and help with the R&D we do. So here's some pictures. This is one of the mirrors from LIGO. It's transparent because LIGO uses infrared light. They look transparent in the optical visible range. They're about this big. These are some of the springs on which the supports for the mirrors sit to help cushion ground motion and keep them from propagating to the mirrors. This is some of the LIGO hardware. This is these vacuum chambers. Here's where the beam splitter sits. Here's where the first mirror of each of the arms sits. And this is about 9 feet tall. These are the long vacuum chambers that go about 2.5 kilometers in each direction. So let me tell you a little bit about our current run. We started this run a year ago, November, at this full design sensitivity I mentioned. We want to collect about a year of live time data with coincidence between the two sites, having both sites be operational at the same time for a total of a year. That will take us till the end of this coming summer. We're searching for signals in the audio band, about 50 hertz to a few kilohertz. The run is going extremely well, to say the least. For example, at the beginning of the run, we had a goal for our interferometers for our sort of standard candle source, which is a pair of neutron stars, each with a mass of 1.4 mass times the mass of the sun. At the beginning of the run, and our goal for the run was to have the range of the interferometers, the ability to see a signal from a certain distance out in the heavens, to be 10 megaparsecs, about 35 million light years for the two long interferometers, and about half that for the short interferometer. During the run, as you'll see in a second, we've made various tiny improvements, and the range, the distance with which we can be sensitive to a source, has increased by about 50% during the past year. So step by step. So this, for example, shows the range in megaparsecs. Here's 10, here's 12 for the long interferometer at Hanford since the beginning of the run, November 8th last year, to now. And you can see it goes up in steps, up in steps. And in fact, here's the latest step. A few weeks ago, we installed some additional apparatus that helped reduce the seismic effect and the ground motion effect, and the range of the interferometer went up about another megaparsec, about another 3 million light years. In fact, it's now, this is from last week, that interferometer is now running at about 15.5 megaparsecs. It's a record for us. It's the best it's ever been, and it's just been rock solid. So the run is going extremely well. Here are the other interferometers. You see the steps as we've made improvements. Somebody at lunch asked me about the duty cycle, what fraction of the time the instruments are on the air. And this, for the three interferometers, H1 and L1 are the 4 kilometers, H2 is the 2 kilometer. And you can see the fraction of the time it's been on since the beginning of the run. And you can see there are ups and downs. There are times we've shut down. And there's this time during the summer, last summer, when it was really beautiful for months at a time. The weather was nice. There weren't storms. And LIGO ran at sort of 85% or 80% duty cycle for each of the interferometers, which is our goal. So it can be done, but when the weather is lousy, when there are lots of winds, when there are storms, it's not always this good. I won't show you this slide, but basically we are now about 2/3 of the way to complete this run. The run should be over in September 2007, and our average, our coincidence between the two sites is somewhat above 50%. We'd like it to be a bit higher, but this is what it is. Okay, so that's the current run. I'll show you some results in a few minutes. There's another step coming. It's a modest thing as far as funding and effort goes, but it's something we call enhanced LIGO. And it will allow us to increase the sensitivity by about a factor of 2, to bring those curves about a factor of 2 lower, to allow us to see a factor of 2 further into the universe. If you see a factor of 2 further out, you see 8 times the volume. And so by doing this, we'll see potentially 8 times as many sources of gravitational waves as we do now, increasing the chances of a discovery by a factor of 8. So it's a very important step. There are a number of things that we'll do, but the main thing is to increase the laser power by about a factor of 3. And we're working on that now, and we expect the hardware for this change to be in place for another science run in 2009. So in 2009, we should have something like a factor of 10 or so more sources, a factor of 10 better chance of making a discovery than the current configuration. And then there's the big step, advanced LIGO, which is advanced LIGO is a major step, and it's not just a step towards discovery. The goal of advanced LIGO is not to discover gravitational waves. We hope to do that before then. But it's to really provide us with enough sensitivity that we'll be seeing gravitational waves on a very regular basis, and using them to interpret the astrophysical sources that produce the gravitational waves, to really pioneer a new field of gravitational wave astronomy and astrophysics. And so to do that, we need a factor of 10 increase in sensitivity, which means we can see 10 times further out into the heavens, which means there are 1,000 times more potential sources in range. And at that point, we would expect to see signals at a few a day to a few a week. And so we'll be beyond the discovery phase. We'll be using these signals to study the sources and their characteristics, really doing astrophysics. The key to advanced LIGO is to increase the power of the laser. That is the number of photons. Remember that factor of 10 to the 21st? We want to increase it by another factor of 20. That allows us to measure where those mirrors are with corresponding accuracy. So, advanced LIGO is ready for construction. We fully expect to start in fiscal 08. Advanced LIGO is in the President's budget. It's the only new start from NSF in the President's budget. We're very pleased with that. We had a baseline review last May and June, and basically the panel was really impressed and said we are ready to start, and that looks like what's going to happen. And so we are now just gearing up and getting ready for this construction start in something like 6 to 9 months. This diagram is a picture of the seismic isolation system for advanced LIGO, for one of the mirrors. And the only message I want to leave with you, it's a layered system. The mirror sits on pendula, sits on very narrow fused silica fibers, so it acts like a pendulum. So it doesn't like to swing at the frequency we're looking for the gravity waves. The pendula are attached to a structure with springs in them that try to damp out any seismic isolation. So there's something like a factor of 10 to the 7th reduction from ground motion to motion on the mirror in the bandwidth that we want to do measurements with these many layers of isolation. And that's one of the keys to advanced LIGO, in addition to increasing the laser power. So advanced LIGO will start in the fall. Its construction is scheduled to end in 2011, and the schedule includes 11 months of schedule contingency. The cost is given here. It's $205 million from the MREFC account, which includes inflation and contingency. And in addition, there are contributions in kind from our collaborators in the UK and Germany, totally worth about $24 million. So this is sort of this big picture of the scientific evolution of LIGO. There's the current science run, which is in progress, about 2/3 completed. Just to give you a flavor, using our standard neutron star binary pair, there are now several hundred galaxies in range at the current sensitivity. I'm always asked, are we going to discover something this run? And the answer is possible, but not likely. My guess is something like 5 to 10% chance. The next step is this enhancement program, which increases the sensitivity by a factor of 2. You can see current LIGO here. Here's the enhancement in this picture of the universe. 8 times more galaxies in range in the year 2009. So we'll be seeing thousands of galaxies. 8 times this number starts to get to be a pretty reasonable probability of a discovery. And then there's advanced LIGO, which increases the sensitivity a factor of 10, gets 1,000 times more galaxies in range. Now we're talking about millions of galaxies. And then we're looking at signals 1 a day to 1 a week. And so here we're not trying to discover gravitational radiation, we're using it as a tool to do astronomy and astrophysics. So that's the evolution of LIGO. Let me give you a feeling for some of the results we've published recently. This is just to give you a feeling of the previous runs of LIGO. I said earlier that over 5 years the sensitivity has been brought down orders of magnitude. These curves show the sensitivity for each of the runs. 2002, early 2003, late 2003, 2004, and now 2005. So as the sensitivity has gone down, of course, the science has gotten better, but also you should notice the length of the previous runs have been measured in tens of days. The current run is over a calendar year. Okay, so a few things about the analysis. There are different classes of signals we're looking for, and so there's sort of different analysis algorithms. There are these binary coalescences, the pairs of neutron stars or black holes, and there we actually have models of what these chirp waveforms would look like. We try to map that onto the data. There are transient sources, bursts, supernova going off. There's no clear model of what the waveform would be, so we have to look for just burst signal to noise in the interferometers and look for coincidences between the two sites, so they're not nearby disturbances. There are continuous wave sources like pulsars, where we actually know something about them. We know the frequency, and we know the details from astronomers. And so with the right Doppler corrections to take account for the motion of the Earth around the Sun and the Earth's turning on its axis, we can lock into those signals and look for gravitational waves at those frequencies. And there's the stochastic background, the burbling, which might come from the Big Bang. And there we have to look for correlated signals between two interferometers. So there are different approaches for the different types of signals. So let me give you a flavor then for some of the results. So first of all, let me talk about the searches for compact binaries. There have been some results from the previous runs, S3 and S4. Here you see the signal. See the red part? That's the chirp. The frequency gets higher and the amplitude gets higher as they spiral together. When they start to merge, the character of the signal changes, and then there's this ring down, which looks like a damp sine wave, as the two objects merge into a single black hole and settle down to a quiescent state. So we use modeled waveforms to filter the data. The data is sensitive to binaries with masses between both masses, either between about 1/3 of the solar mass, or between 1 and 3 solar masses, or between 3 and 80 solar masses. And so in our S3 run, we took about 10% of a year's worth of data. And what we could see by integrating over time and the distance we were sensitive to was about the equivalent of 3 Milky Way galaxies for our canonical source. For S4, the run was shorter, the sensitivity was better, so we could be sensitive to about 24 Milky Way equivalent galaxies in that run for the neutron star case, and about 150 Milky Way equivalent galaxies for the black hole case. That is, the objects having about 5 times the mass of the Sun each. For the current run, S5, we have analyzed data for about 3 months of the run. As I said earlier, we have not seen any signals, but for the black hole, for the neutron star case, something like 200 Milky Way galaxies equivalent numbers of stars are in range now, and for the black hole case, about 1,000. So you see, as we run longer and as our sensitivity improves, we sort of integrate over more and more galaxies, more and more potential sources. We set better and better limits. And this plot shows you that for the current run, for the 3 different interferometers, as a function of the total mass of the pair, this shows how far we are sensitive out into space. And so the peak, for example, is at 130 megaparsecs. That's about 400 million light years for a pair where the total mass is about 25 times the mass of the Sun. It just gives you a feeling for how far out into the universe we'll be sensitive to by the end of this current run. Okay, the next plot is for what we call untriggered gamma ray burst searches, just looking for something going boom. Again, we haven't detected anything. This plot shows it's sort of the rate limit as a function of our sensitivity in strain, in the thing we measure with the interferometers. This is the kind of signal we might look for a burst. And the point here is simply that as the runs have gotten longer and the sensitivity has gotten better, the strain sensitivity improves, and our sensitivity to a possible source gets more and more sensitive. Just to give you a flavor for that, in the current run, we would be sensitive to some kind of burst, say a supernova, which put about 1/10 of the mass of the sun into gravitational waves at a distance of about 60 million light years. We've also looked in our gravitational wave data for signals in coincidence with external signals, like gamma ray bursts. So when we learn about a gamma ray burst from SWIFT or one of the satellites, we look in our data at the same time to look to see if we see a gravitational wave signals. And so far, we haven't seen any, of course. We've done this for both the previous runs, S2, S3, and 4, where we looked at a total of 39 gravitational bursts, gamma ray bursts. And for the current run, about another 53 gamma ray bursts. And so we've seen no signal in coincidence with those. Our typical sensitivity is that if a third of the mass of the sun were put into the gravitational wave energy signal at 20 megaparsecs, we would see it. Again, to give a flavor of the sensitivity. We've been looking for pulsars, looking at known pulsars. And there are a few interesting results here. One interesting one is the Crab Nebula. This plot shows our sensitivity, our sensitivity as a function of frequency, and these plots are the limits we're setting for various known pulsars. One interesting one is the Crab pulsar. For the Crab pulsar, our limit is shown over here. It's just below the 60 cycle noise, but it's right over here. This triangle is what's called the spin down limit for the Crab pulsar. The spin down limit, we know the Crab pulsar and other pulsars are spinning down, losing energy. And if all their energy were to go into gravitational waves, all the energy lost in that spin down process were in gravitational waves, there would be a signal over here where the triangle is. So we're about 60% of that now. So this becomes astrophysically interesting in terms of setting limits on what fraction of the pulsar's energy loss goes into gravitational waves. We're also able to measure the ellipticity of pulsars, because if they're spherical, there's no signal, so we can set limits on the ellipticity. And our best is one pulsar with an ellipticity of 10 to the minus 7th. Pulsar is typically 10 kilometers in size, so an ellipticity of 10 to the minus 7th means there's a lump 1 centimeter size on an object 10 kilometers in size. This is the data and the results for looking for stochastic signals, which we might interpret as limits on the amount of energy from the Big Bang in gravitational waves. Omega in this plot is equivalent to the energy it takes to close the expansion of the universe, the critical energy in the universe. From our early runs, these limits were not very interesting, 44. But now, from the previous run, we have a limit we're publishing, which is 6 times 10 to the minus 5. And this starts to become interesting because it's just about the point that will challenge a limit set by Big Bang nucleosynthesis. And so by the time we get to the end of the run, we'll probably do another factor of 10 better on this and improve on the limit, which is now set by Big Bang nucleosynthesis for the amount of energy from the Big Bang in gravitational waves. So that's an interesting result. Advanced LIGO in 1 year will bring this limit down from now 10 to the minus 5th to 10 to the minus 9th. Is that interesting? Well, there are ideas about cosmic strings which predict signals at 10 to the minus 8th, so that's interesting. The standard inflation for the Big Bang predicts 10 to the minus 14th. So that's out of reach for us. But there are some other models about things that went on before inflation that give predictions which will be in our range. So we might see something, we might set limits. But it becomes interesting as far as cosmological origins go. So let me now talk about the international scene. There are gravitational wave interferometers around the world. Here's LIGO at Hanford, here's LIGO at Livingston, Louisiana. And these are our current colleagues in the world. GEO is a British-German interferometer in Hanover, Germany, I'm sorry. It's 600 kilometers long. GEO has, for a few years now, has been integrated into LIGO. We share our data, we analyze data together. The GEO scientists are part of the LIGO scientific collaboration. So they're at worst first cousins. They're part of our family. Virgo is an instrument that's 3 kilometers long, located near Pisa, Italy. It is being commissioned now. It's starting to achieve its design sensitivity over some of the frequency range, and we've been trying to work very close to them, and we've just negotiated an agreement with Virgo to share data and work together. And so what will happen starting in a few months is that LIGO and Virgo together will analyze the data from all of our interferometers. We'll publish together. We will have the advantage then of having more eyes on the sky, having a higher probability of 2 sites being on the air. Since there are 3 sites, we'll coordinate our operating, having a higher probability of checking a result if we see one. And we'll then also have the additional ability of triangulating. And if you want to know where the waves came from, you want to be able to triangulate on the sky, have three eyes looking up there. So this is a big step. The Japanese have an instrument near Tokyo called Tama, which is 300 meters long. It's more of an R&D test bed. And the Australians have one near Perth. So that's the current situation. I think I've told you this. The future is really one of expansion. Advanced LIGO, as I mentioned, will be operating in 2014. Our colleagues at Virgo want to build Advanced Virgo, which will match Advanced LIGO in its improved sensitivity on the same time scale. Our colleagues in Germany and the United Kingdom want to upgrade GEO 600, the one in Hanover, to improve its response at high frequencies. The Japanese gravitational wave community is proposing a large cryogenic interferometer in the Kamioka mine in western Japan called LCGT. There's a proposal in now to their funding agencies to get support for that. The Australian gravitational wave community is working towards IAGO, which would be a 5-kilometer interferometer at their site near Perth. And so hopefully in the future there will not only be LIGO and Virgo, but an improved GEO, a Japanese facility, and an Australian facility. And we'll all try to work together as an international network. At the same time, we're all working on developments looking ahead to a 3rd generation set of facilities, something beyond these. Who knows what that will be someday. Okay, so that's a story about LIGO as far as gravitational waves go, but I want to spend a little bit of time about education and outreach, because this is a very positive story that we all care about, I care about a lot. And there are several elements to our education and outreach program. And let me tell you a little bit about our Science Education Center. This is a center that's recently opened right at our Livingston site. It's funded by an NSF grant. You'll see some pictures in a second. It's a big facility, about 8,000 square feet. And its focus is not only public education, not only education of students, but it's also a very important regional resource for teacher training and development. And a lot of its focus is on teacher training. We've done this with partners from Southern University who have a very active teacher training program. The San Francisco Exploratorium, I don't know if any of you know it, but it's one of the premier science museums. And they've, with this grant, have provided about 50 hands-on exhibits for our science center. So it looks like a mini exploratorium. And LA Gear Up, which is a state educational reform agency, that's part of the Louisiana State Board of Regents. So with these partners, we've set up the Science Education Center, set up the exhibits, set up the training capabilities. We have through Southern an inroad to teachers people who are being trained to be teachers, through LA Gear Up to active teachers who can come and learn more about science and teaching science especially. So this is a picture of the Science Education Center. This is the final bit of construction, and the reason I showed this is you can maybe see it here. On the facade is a wall with about 100 of these very large aluminum beams. And I'll tell you what that's about in a second. But I should tell you, we learned a few days ago that this building received the Award of Honor from the American Institute of Architects, their New Orleans chapter. And the award said, I can't spell, form and function come together in an exciting and unexpected way in this building, which has a dynamic exterior wall that suggests its purpose, a science education center. This wall waves in the wind. So this is some pictures inside the Science Education Center, a bunch of kids with our giant slinky. It's infinitely fun. These are some of the exhibits which were constructed by the Exploratorium. And so if you've ever been to San Francisco and gone to the Exploratorium, you can just imagine what this is like. So our education and outreach program in Livingston is focused on the Science Education Center. But we also have an active program at Hanford, at our other site. And they describe their mission as bringing the public out to touch and see science in the making. First of all, see real scientists, come to a real site where science is done, see the control room. But there's also activities that involve teacher training, school tours, astronomy nights, things of that sort. And there are large numbers of people come to the site for these things. For example, in the school year 2005-2006, there were about 3,000 visitors, including almost 1,000 K through 12 students. Other things have happened. There's been the Einstein's Messenger DVD, which is this wonderful Nova quality video about LIGO. This was developed as a supplement, as material for the classroom, and we've with that developed some supplementary material for teachers to use in the classroom to go with this. We're getting very positive press, which is very important for LIGO, and in some ways a fairly new thing with big articles in the New York Times, and the LA Times recently. And Einstein at home. So this is our way in which everybody can participate in LIGO data analysis. It's modeled on SETI at home. It's now one of the world's 3 largest distributed computing projects. And if you can see this, it's a map of the sky with stars and things. You can see these 2 V's are the 2 LIGO sites, and a user will donate their spare computing cycles to LIGO and analyze data. So for example, this user will be analyzing data in this little band on the sky. And the data that's being analyzed is an all-sky search for pulsars. The results I spoke to you previously about said, we know there's a pulsar there. We know its frequency. We can look there. But let's say we want to look for pulsars that are unknown, or signals from pulsars that are unknown. You have to look all over the whole sky at all frequencies. That takes a humongous amount of computing power, which we don't have. So we have the public now working with us on this. And so there are about 150,000 people who've donated their computer time, almost 1/3 of a million machines. We have about 80 teraflops of CPU, 7 days a week, 24 hours a day working on this. So here's the sort of summary. LIGO is operating at our design sensitivity. And this is a very, very big deal after all these years. And it's really a tremendous achievement. The current run is about 2/3 complete. No detection yet, but there are very interesting astrophysics results coming out in terms of the limits we can set on possible sources. The next step is to increase the sensitivity by about a factor of 2. So we get 8 times as many sources in range. And the big step is advanced LIGO, where we'll have 1,000 times as many sources in range. And so this will be our progression from discovery through doing gravitational wave astrophysics. We're also leading the effort to put together this international network. We've now got links with GEO in Germany. Very recently, these very tight links with Virgo in Italy. We're working with the Australians, and we're working with the Japanese to try to make sure in the future, when they have their facilities, they can join us. And finally, I believe we have a first-class education and outreach program anchored by our Science Education Center.